So let's recall what we have learned last time. So this one has two forms. First one, the first formulation for this fundamental theorem of calculus is that if we consider a continuous function and then the definite integral on a varying interval, the resulting is a function of x. This new function is differentiable and the derivative is exactly f. So we can rewrite this as the derivative of the definite integral with varying upper bound recovers the function. So in this sense, the integral and the derivative, they cancel each other. Second form, still the theorem, just two different forms. We consider an antiderivative of this function. Then we have the definite integral equals to the difference of the antiderivative at the two endpoints. So we will use a short notation for this, new notation. Whenever you see some quantity with a bar, lower limit, and upper limit, it means the difference of the values at the two endpoints. The upper one subtract the lower one. Okay, so now we can see to find the integral of a function, we don't have to go through the limit process. If we can find an antiderivative on this interval, we can use the antiderivative to evaluate the integral. That's what we did last time, for example. Without the theorem, we have to use the definition. We make a partition, have approximate areas, add them, then we take a limit. And now with the theorem, we just need to find an antiderivative. And for this one, we know what the antiderivative is. So e to the x will be the difference so finding this integral becomes easy if we can find an antiderivative. However, so the tricky part is it's not always easy to find the antiderivative. We need a lot of tricks, techniques, method to find the antiderivative of some more general functions. And we will learn more about that in the next chapter. Okay, now I have two ELISA. Okay. And a slightly more general formula. Let's double check. Okay, let's recall how do we find the derivative of this one? Zichen, do you remember the formula? Okay, so this one, this will be the composition of this function with the gx. When we take a derivative, it will be the derivative of the exterior function at gx with the derivative of the interior function. Okay, so chain rule. Derivative of the exterior function is f at gx, and the derivative of interior function. In particular, in the previous case, if we replace this g by x, this will be x, and the derivative of x is 1, we recover the formula. But we can build it as a special case. Another one. Sophia, do you remember the formula for this one?
Do you also use the chain rule?
Yes. Also use the chain rule. So the difference is for this one, when x increases, the interval becomes longer. But for this one, when the position increases, the interval becomes shorter. So this, in this way, they introduce a negative sign. And again, the chain rule will be the derivative of hx. Okay, the first one varying upper limit. Second one varying lower limit. Now we will combine them. Elisa, how do you find this derivative?
You add them the person.
So this one, both this changes and this changes. One way to find the formula is we can, so suppose this is G, I'm sorry, this should be lower. Let me draw a picture. Gx of lower limit should be hx. To find this limit, we can break this integral into two parts. first one and second one. When we take a derivative, there will be the derivative of this first part and with the derivative of second part. For the first part, it's the same as we had over there. We will have this part of the derivative. And this is similar to what we had over there of this derivative. The result will be the combination of the two. Okay, so one from here, other one from there. That makes sense? Okay, now have some practice. Practice, let's find the derivative. I'm going with minus x. Make it, okay, let's try the simpler one. Okay, let's find the derivative of you. Okay. Sophia, where do we start?
You do f of g of x.
So in this case, what is f?
F is t squared.
T squared, but now we use x variable, so we use this. Okay, let's keep t. Maybe t is fine. T squared gx e to the x hx sine x. So this will be f something square g is e to the x square. And the derivative of e to the x is another e to the x. Zichen? All right, okay, yes. So this is the rule. We can simplify it a little bit e to the 3x. Okay, that's the derivative. Okay. And another important formula, the linear property, the integral a fx so the next one, let's introduce this 5.4 indefinite integrals. It's close related to what we have introduced before, but slightly simpler. So we call this, initially we have this a function we can find is a derivative, but we can also find the antiderivative. Okay, so this notation, we can use it to find the definite integral, but we introduce a new letter for this to make the connection more transparent. We introduce this. The indefinite integral. it's fx x. The main difference between these two notations is this is more closely related to f, maybe more transparent. We don't have to introduce a new function. Moreover, so this definite integral, as we have said before, is the difference. We can view this as the evaluation. So this definite integral can be viewed as the evaluation of the indefinite integral on this interval. So plus c, the plus c, if we evaluate at a, it's still c. Evaluate at b, it's still c. So c minus c equals to 0. So initially it's f b plus c minus f a plus c. They cancel each other. We end up with, yes, a very good question. Okay, let's have some practices with this new notation. The definite integral of x cubed squared. Okay, Zichen. The indefinite integral. It will be the antiderivative plus c. Okay, so that's the indefinite integral. Let's try another one. Sophia, the indefinite integral.
E to x plus c.
Elisa. Indefinite integral.
Yeah, you do cosine x plus c.
Okay, so you know this negative cosine x c. Okay, so a formula for this is the linear property. If you have a linear combination, a fx b gx, then we do the indefinite integral. This is the same as the linear combination of the indefinite integrals. Okay, again, this follows from the linear property. That's easy, we skip the proof. Let's find the following. Indefinite integral x e Okay, that was so easy. Let's think about it. How do we find this one? Where do we start? The indefinite integral of these complicated functions. So first, yes, we will do that. First step, we break this one big function to three simpler functions, three simpler integrals. And see the linear property of this indefinite integrals. Indefinite integral of the combination is a combination of the indefinite integrals. Okay, Sophia, the first one.
It is
X cubed.
1/3
1/3 or something else?
1/4
Okay.
x 4
Okay. So we will plus C. I will put all the C at the end. And Elisa, next one, e to the 3x.
E to the third times
3 or not?
yeah. Wait.
If we uh-huh. Is this the derivative or the integral? Okay, what should it be? Should be something, right?
1/3.
Okay, yes, yes. So how did you get 1/3?
Because
Because when we take a derivative of this, it will give us another 3. So 3a equals 1. The a must be 1/3. Okay, so that's the maybe. So I want to say e to the 3x equals a is 3x. We don't know what this a is, but what we know is the derivative equals a 3 is 3x. And we wanted this to be e to the 3x. It implies 3a equals 1, a equals 1/3. That's how we find the coefficient. This should be 1/3. Okay, Zichen, last one. Guess one. Let's guess a formula. Almost, almost. But say, if you take a derivative of this, what do you get? So you have this additional 3. How do you cure it? Okay, okay. Now see, we have to. Okay, technically, we will have a C for this one, another C for this one, a C for this one. Because this C are just integral constant. So what is this C? It stands for integral constant. So there's 3C over here. We can use one integral constant. Okay. So this will be the integral. Okay, now we have the indefinite integral. Let's compute the definite integral. Okay, Sophia, how do we find this definite integral?
Mm,
We found the indefinite integral. Okay, by the formula, it will be the difference of this at the two endpoints. So we can copy this function, then find the difference at the 0 and 1 will be at 1 we have 1 1 at 1 at 1 at 0 at 0 then we simplify. This will be 1/4 1/3 E3. Well, this will can just 1/3 cosine 3 minus 0 1/3 and 1/3. 1/4 minus 2/3. This will be of 8. Okay, definite integral. Okay, any questions so far? Okay. Uh-huh. So this comes from what the meaning of the C. C is not a number. It just stands for the integral constant. It depends on if you choose 1, you get one antiderivative. To 0, another antiderivative. To the 100, you get a family of antiderivatives. The difference is just a constant. So it's your choice. It could be anything. Okay, so just because here we have 3 integral constant. Can just use one of them because it's a constant. This 3, 1, let's see, this will be 1, 5, -2. Now I just have 4 over there. Sophia, questions?
no.
Okay, and Elisa?
No.
All right, okay. So move to the next section. A very useful rule for doing integration. Substitution. Okay, so when we do this integral fx dx, so this x is an indication for the integral variable, but we can also use a different variable. We could use ft dt will be the same thing. F u du. They all represent the same thing. So sometimes we call this a dummy variable because it doesn't matter what you call it. You can call it x, you can call it t, you can call it u. It doesn't matter. Similarly, if we do this summation, we can also use different variables. We can use I from 1 to n, I squared, mean the same thing, but sum the squares. You could use j, 1 to n, j squared. So in this case, the k, I, and the j is dummy variables. It doesn't matter what you call it, as long as you know how it changes. Change from 1 to n, then it's all the same. Okay. Next one, we want to find the interval. Okay, let's try to think about how do we find this indefinite integral. According to our theorem, we need to find a function, find an antiderivative. Antiderivative. Have we seen anything like this before? A function with a derivative is 2x times square root of 1 plus x squared.
Maybe.
Okay. Okay, so it's not easy to do this directly. So what we do? Let's record the following. Make it slightly simpler. Anyone can tell me this formula?
It is
I'm going to change it to x, so it may be more convenient.
so that is the same as x to the power of 1/2. So it will be 2/3 x to the 3/2.
Okay, so we have this constant. We know this. We want to use this result as a guide for the previous one. For this purpose, we introduce a new variable. So u equals 1 plus x squared. If this is the u, what's the derivative? Zichen? How do you take a derivative of this with x? Okay, so you have 2x. Okay, with this new information, let's rewrite the integral we are looking at. I'm going to change the order a little bit. Is x squared. I copied it wrong. Now under the square root, we have this new variable. So I will replace this by u. It's the same thing. Then we deal with this 2x dx. So here, if we view this as the quotient of du with f dx, we can rewrite this as then we recognize what we have over here can be replaced by du. Elisa, do you agree?
Yeah.
Okay, because they are the same, I'm going to replace this by du. Okay, Zichen, could you find an antiderivative for this one? The integral of this? Square root of u du. Let's compare with, what's the difference? So what's the result? Okay, so this step will reduce the integral of a complicated function of x to a much simpler function of u. We find the integral. Then we can switch back to x. U is 1 plus x squared. It will switch back to a function of x. We find the indefinite integral. So this process, we call it substitution. Sometimes we want to emphasize this u variable called the u sub. The method. We can write this as more explicit substitution. If our integral is of the following form, as we have seen before, the f will be the square root. And the gx, for this example, is 1 plus x squared. The derivative is the derivative. Then we can substitute. Okay, so if our integrand is of this form, the composition with the derivative of the interior function, we can use the substitution because we can check du dx g derivative x, so du g derivative x dx. We can substitute this by du gx by f by u. Then this very often is much easier to integrate. Okay, so let's redo what we have done before and use this new method. Okay, so we can view this as the composition of exponential function with 3x. What's missing over here is the g derivative. So if g is 3x, what's the derivative, Sophia?
3.
Just 3. Okay, to make this the form what we wanted, So I will make up the 3 over here and then divide by 3 in the front. Are they the same? Okay, they are the same. Now this will be the composition function. This will be the derivative. So I will use the substitution. One third e to the u du.
Oh,
Okay, Sophia, what's the integral of this one?
it's 1/4.
Oh, no. So this is u. Okay, maybe let me rewrite. Let me rewrite. So this is our variable u. So how do you write u? Maybe like this? Is this better?
It is
E to the u.
e to the u, just e to,
Uh-huh.
yeah.
Okay, so this will is 1/3 e to the u plus c. And the last step, we switch back to x. 1/3. This is where this 1/3 come from. Coming from this substitution, we're gonna make up the derivative of it. Okay, a similar one. Okay, again, let's try to applying this substitution rule, see what you get. Okay, Elisa, how do we start?
You add.
Okay.
Wait, you multiply by a 3 and then divide by.
Okay. Again, we will have this 3x, so I will make up 3 over there, then to keep this an equation, I divide by 3. So now we can use the substitution. Zichen, what's the indefinite integral of cosine? Sine u. And we switch back to x. Okay. Okay, next one make it a little bit more complicated. Let's try this. X squared. Okay, what is the gx? Sophia, what would you pick? How to make this function appear simpler?
You can
Let's go back to the previous one. Let's make a comparison. In this example, what's our u?
square root of u.
So u is what happened
Oh,
onto the square root. With this choice, this function becomes much simpler. So here, what u would you pick to make this simpler?
x cubed plus 5.
Okay, so that's our first choice. If we have this, what's the derivative?
It's x to the power of cosine u.
So how do you take a derivative of this?
3x squared.
Okay, 3x squared. Okay, now we have x squared. So what's missing is 3. Again, we will make up a 3 and divide it by 3. Cosine. Okay, now we have u and du. So we can rewrite this using the u substitution. Okay, Elisa, what's the integral of this one?
Negative sine v plus c.
It will be okay, so at this step is exactly the same as what we had before. However, when we switch back to x, we have a different x. For the previous one, u is 3x. We switch back, we have this. In this one, u is x cubed plus 5. So Zichen, what's the last step? Okay. Okay, so this is the u substitution. Okay, a little bit. Oh, let's try another one. What is our function? Okay, first let's try. Could you find a function whose derivative is logarithm x over x? Okay, so it's not easy. So we will write this as the product Okay, so now we want to use substitution. So some function whose derivative is 1 over x. Sophia, any function whose derivative is 1 over x.
Natural log of x.
Okay, so we can pick du dx du. Oh, I move this back here. We have this will be our u, and this will be du. Elisa, an antiderivative for this one. And Zichen, how do you do this one? And okay, And Sophia, if we switch back to x, what do we get?
1 half ln x squared plus c.
Okay, now can see we find something very interesting. The derivative of this is logarithm x over x. Highly non-trivial. Okay. And the last few minutes, we learn something about the symmetry. Consider a function defined on a symmetric interval. And we recall the even function if the same value, odd function if it has opposite value. Then when we do the definite integral of the symmetric functions on a symmetric domain, if it's an even function, then we say it's twice of the integral. Oops, that's rewrite. If it's an odd function, the reason for this is if you look at the picture, if we have an even function, then this area the integral from negative a to a, this total area is twice of this area because they are symmetric, they have the same area. If it's odd, okay. Then, oops, wrong option. If it's odd, then this part has the same area, but with opposite signs. Over there, f is negative, f is positive. This, they cancel each other. So the integral overall will be 0. On symmetric domain, the integral is twice of the positive half if it's even, and 0 if it's negative half. Okay, try one example. Okay. For this one, we could find the antiderivative, but we observe this one is even and this is odd. This one even and this is odd. So by the symmetrical property, twice and 0. Which will be 2/7 over 7. Okay, so that's the integral. Let's have a 5 minutes break. We'll be back at 11:01. Okay, so let's start. This is about the chapter 5 integrals. In chapter 6, we only cover a few topics in chapter 6. So applications. Okay, so previously we defined, maybe we introduced the integral as the area under the graph. Under the graph. Suppose that we have a second function. That is less than f. We want to find the area in between. Okay, so Chen, do you have a formula for this area? And why is that? It's uh-huh. Okay, okay. So there are different ways to explain this. We can view this as the difference of the total area subtract the smaller area. Okay, that's very simple formula. Under the assumption that fx bigger than gx on this interval. Now a different situation. Similar, but slightly different. Okay, Sophia, now we have a function of x depending on y. The graph is look like this. Could you give me a formula for the area of this region?
The you find the integral of the inverse? Or
You mean do you want to find the inverse y equals inverse x, something like this?
Yeah.
But in our case, this function failed this vertical line test. It's not one-to-one, not invertible.
Mm.
So
Yeah.
what should we do? In this case, we can do the integral instead of on the x direction, but we on the y direction. We integrate from c to d of this function with respect to y. You can do the partitions, do the summation to the limit, essentially the same. Area on the left of now we have a second function. X Elisa, are you back? Elisa? Okay. Could you give me a formula for the area of this region?
Integral of fy minus integral of dy.
Okay, it's yes, the same logic. Under the assumption. Okay, so these two cases, if we have this clear picture, the formula can be given easily. But sometimes it's not that clear. And consider the following case. So let me find our function. Graph the following: y equals x and get the check. The first function, what's the graph of this function? Okay. And Sophia, what's the graph of the second function?
There's an x-intercept at x is 0 and x is 4.
Okay. So it's a flipped parabola.
Yeah. You
Okay.
can find the vertex if you write it in vertex form.
Okay, so let's find the vertex. Okay, so what's the vertex?
2, 4.
2, 4. Okay. Okay, now if we look at the picture, we see a region enclosed by the two graphs. How do we find this area? we want to apply one of the formulas. This one seems appropriate. To apply, we need to find A and B, where we start and where we finish. Where we start at 0, where we finish. Where do we stop? Stop here. What's this point? Not easy. So, Sophia, any idea how to find this point?
You set an equation. You say y. You say x equals 4x minus x squared, and you solve for the intersection point.
Okay, now we have the points. This one is 0. This one is 3. So our integral, the area equals 0 to 3. Okay, which one is F? Which one is G? Who subtract which? Who? Okay, Alisa.
The red one subtracts the blue one.
So the red one is 4x squared minus 4x. Subtract the blue one, bx. Okay, I will give it a few minutes to find this integral. Where do we start? We first simplify the interior. What's the function? Four x minus x. Okay, that's 3x. Okay, 3x will be from 0 to 3. At the 3 is third. At a 0, they're all 0. It's just 7 minus 9. So be 2 over 9. Now we took so the area bounded by these two curves. The function is 9 halves. Okay. Check my answer. Any mistakes? So sometimes I made mistakes. If you say something, let me know. Alisa, do you get the same answer? I got a different one.
Same.
Okay, so that's confirmation. Second application is what you may have learned in physics called work. We start with a special case. We move an object along the x-axis from A to B with the force F So we have Newton. It's meters. Then the work. Okay, let me check. Sophia, have you learned this in physics before? The work done by the force moving an object in one direction.
Maybe.
Okay. And you learned this. Okay, so the formula it will be the product FD. The unit of this will be joule. Joule. Sometimes we use this just G for joule. Okay, if I have this constant force, that's the formula. If the force changes in the process, we will have the integral. In this case, the total work is done. So we use this integral. Okay. So if we can do the integral, then we can use this formula to find the work done by this force. Okay, so this is a brief introduction about the integrals. The how to do the integral, that's a very hard topic. In chapter 7, we learn quite a few different techniques to do the integral. Okay, so this for many of you, this will be the most difficult chapter so you have so far. Or more difficult than what you will have learned. And if you recall when you learn this derivative, it's very natural. You give a function, you take a derivative, so not so much trick. You have some rules, but not so much trick than taking derivative. Many people, what's the difference? When you take a derivative, you have the function, you don't have to guess what you will do next. But for this integral, you don't see the antiderivative. You have to guess and try to find it. The first technique is if you have two parts of complicated functions, we want to convert to something slightly simpler. 7.1, very important method, integration by parts. So this technique for integration comes from one formula from the derivative, it's called the product rule. Okay, Sophia, what's the formula for this product rule? Unmute this one.
F times derivative of g of x and plus g of x times derivative of f of x.
Okay, so sometimes I will use I just make 2 copies. I put the derivative on the first one and on the second one. So for this formula, I'm going to take the indefinite integral on both sides. Okay, the indefinite integral of this derivative. Okay, Zichen, what's the indefinite integral of a derivative? So now we have a product. We first take the derivative, then we take the integral. What do we have? Yes, the original thing. That's very nice. Original thing will be fx gx. Let's see. So the integral of the right-hand side. This one will apply the formulas. This is the linear property. So they equal each other. So we set up an equation. Very simple analysis, but this is an extremely useful approach. So here we have 2 integrals. And we know what the integral is. Sometimes one of them is easier to integrate. Most of the time, this one could be very difficult. This one could be very easy. Then the integral of this will be this total thing subtract the easy one. So to do this complicated, potentially very complicated integral, we only need to do some relatively simpler one. So that's the power of this integration by parts. Move the hard work on the difficult part to the easy work on the simpler part. Integration by parts. So it is, let's make the assumption if this one is more difficult, we can find the integral. Normally, which one do we seek? Okay, we keep this one. It's the same thing, so this integral. Let me box this formula. Very useful formula. And if you compare these two formulas, two equations, you can see I dropped this constant. Could you explain this? Why could I drop the constant from the formula? So, because this integral comes with an integral constant. This one also have integral constant. So because we have integral signs on both sides, there's no need to write the integral constant until we finished this. After we find this, we may put an integral constant. At the moment, it's not necessary. Okay, some practice. Practice, let's try. Okay, so this time, okay, Zichen, does this feel familiar? Any function whose derivative is this? We have additional x over there. It's not so easy, but if we match this with our formula, we want to apply this integration by parts, f, g. If we, with this identification, Sophia, what is g?
G is e to the x.
E to the x. Now f is x. What's the derivative? Okay, okay. Now let's copy the formula. I don't do anything. I just copy this formula. Copy the formula fx gx f derivative gx dx. Okay, integration by parts. Let's plug in. Okay, the term was f. F, not f derivative. Okay, x. At least I was gx. This will be e to the x minus. Okay, Sophia, what's the f derivative?
1.
Just the 1, and the g is e to the x dx. Now Zichen, what's the integral of this one? Now it's very easy. Since we are done with the integration, we put this integral constant. Okay, so we found the formula. So summary, x e to the x dx is x e to the x. Something new we haven't seen before. Is this correct or not? How do you verify this? Sophia, how do you verify this? Correct or not?
You can.
We'll take the derivative of this one, see if we recover the function. Okay, let's take the derivative. Okay, Zichen, what's the derivative? So for this one, what rule would you apply? Okay, it's a product rule. It's the same. Okay, so it will be 1 e to x plus x is x is to x, and subtract e to the x So you can see they cancel with each other only this left. Okay, and the derivative is what we started. Okay, so this is one simple demonstration of this integration by parts, and we'll have more about it next week. Okay. Any questions? Elisa?